Welcome once again. In this video, we discuss about the Euler's method in numerical analysis. Friend, Euler's method is useful to solve the first order differential equations when the initial conditions are given. So, I will write here Euler's method. Euler's method. Now, using this method, we solve this equation dy by dx equal to f of xy with initial condition y equal to y0 at x equal to x0. When we solve this, when we need the solution of this differential equation dy by dx equal to f of xy with the initial condition x equal to x0 and y equal to y0, then Euler's method is a very useful method. Friend, we know that when there is a small increment in the independent variable delta x, there is a small increment in dependent variable delta y. And the definition of dy by dx is nothing but the limit of delta y divided by delta x, where delta x tends to 0. Now, from this, for very small values of delta x, for small values of delta x, we write this as dy by dx is approximately equal to delta y divided by delta x, or delta y equal to dy divided by dx into delta x. This is an approximate equality for very small values of x. Now, from these small values of x, we can write now dy by, what is our dy by dx? Here delta y equal to dy by dx means f of x comma y, and we consider this delta x is a h, so this will be h into f of x comma y, the value of dy delta y. When we integrate this with respect to so let us take integrate this. Now on integrating, we have the increment, we write in the integration in the form of dy, and it is from y0 to y0 to y1, and here integration of f of x comma y between the limit x0 to x. So integration of this, and integration of dy is dy is y between the limit y0 to y, and integration of this is equal to right hand side as it is x0 to x f of x comma y into dy dx. So we get here integration y0 to y1 equal to y0 plus integration x0 to x1. We consider this point x1 x1, and between the limit x0 to x of f of x comma y into dx. So friend, we have used this is delta x. Now we have integrated this between the limit x0 to x. Whenever x0 to x, at x0 value of y is y0, at x1 value of y is a y1. So y1 equal to y0 plus integration x0 to x f of x comma y into dx. This is an approximation formula. Now we substitute in this approximation formula f of x0 comma y0, so that this will be y1 equal to y0 plus integration x0 to x1 f of x0 comma y0 into dx. x0 y0 is a constant value, hence it is y0 plus integration of dx is x between the limit x0 to x, and f of x0 comma y0 is a constant, and we get y0 plus x1 x1 minus x0 into f of x0 comma y0. x1 minus x0 is a h, so y1 equal to y0 plus h into f of x0 comma y0 plus r, where r is the error, capital R is the error. Now again, f of x0 comma y0, what is f of x comma y? F of x comma y is a dy by dx. So it is x0 y0 is nothing but the value of the dy by dx at x0. So we write it as y1 equal to y0 plus h into dy by dx at x0. We can write in this manner also. Or if we remove this error, we have now y1 equal to y0 plus h into f of x0 comma y0. So this is an expression between the 2 points x0 and y0. At x0 we have y0, at y1 x1 we have y1. Similarly, y2 equal to y1 plus h into f of x1 comma y1, y3 equal to y2 plus h into f of x2 comma y2, or in general yn plus 1 equal to yn plus h into f of xn comma yn, and this is known as the Euler's method. So what we have, or how we have deduced this Euler's method? This is our first order differential equation dy by dx at the point f of x comma y with initial condition x0 and y0. Then we have used the definition dy by dx is nothing but the limit of delta x, where dy by delta x divided by delta y divided by delta x. For small values of x we remove the limit and it will be approximate. Dy by dx is nothing but equal to delta y by delta x, and delta y by delta x we get delta y equal to f of xy into delta x. We have integrated this between the points x0 to x1. At this point x0 to x1 we have y0 to y1, so integration of dy and here integration of f of x comma y into dx, and we get the first approximation, that is y1 equal to y0 plus integration of x0 to x1 f of x comma y into dx. So when we put the particular value of the function at the point x0, it become constant and we arrive at the y1 equal to y0 plus this integration y1 equal to y0 plus h into f of x0 y0. So this will be same at for the point x2, that is y2 equal to y1 plus h into f of x1 comma y1, the next step. Then y3 equal to use this y1 use this y2 in the next step, y3 equal to y2 plus h into x2 comma y2, and similarly yn plus 1 equal to yn plus h into f of xn comma yn. So this is the Euler's method to solving the first order differential equation. Now this method has some drawbacks. When h is a very small, this method is too slow, and when h is a very large, this method is inaccurate. So these are the drawbacks of the Euler's method. So friend, I hope you got the idea of Euler's method of solving the first order differential equations. Thank you friend.